For as long as I can remember, computer nerds such as myself have chased higher and higher clock speeds for graphics cards and computer processors. Big number meant big performance and something to flex on other enthusiasts. But these days, that's slowed down a lot. I remember when I was in high school and a CPU being overclockable to 5 GHz felt like this crazy milestone, and we all kind of assumed incredible performance came of it. But looking at the x86 processor sold today, and 5 GHz still remains the high-end cap, more or less. Yet CPUs are obviously still getting faster and faster. What happened? I'm EposVox, the stream professor, and in 2025, we're getting back to basics. I want to help everyone understand tech better and control how it impacts their lives more. In today's video, I'm going to break down CPU specs, clock speed or frequency, core and thread count, and IPC, and show you how each play a role in the actual performance of your computer. All of this is with the help of this video's sponsor, ARM. ARM's compute platform powers 99% of today's smartphones, and ARM touches 100% of the connected global population through phones, smart TVs, tablets, server infrastructure, and even the keyboards I use, and my 3D printer, and my music pad, and a bunch of other stuff. Let's start with the physical description of traditional x86 processors like you'd find in a desktop PC. The primary thing you hear about and consider when shopping for a desktop processor is core count and thread count, at least for desktops. For many workloads such as video editing or 3D rendering, more cores and threads equals higher performance, at least to some degree. But there are plenty of scenarios where processor A has many more cores than processor B, but performs worse for video editing or gaming tasks. Typically, processor A in this scenario is built for server use rather than desktop use. But why does this happen? Why does this matter? And what even are cores? Cores are basically individual processors. In some contexts, you may hear individual cores of a CPU be referred to as different CPUs in terms of the specs. A standard desktop x86 processor has multiple physical cores, plus additional hardware for handling communications with system memory or DRAM, throughput controllers, and for PCIe lanes and USB ports and so on. But the cores themselves are the actual processing units that execute instructions, perform calculations, and things like that. This is why, in many cases, more cores can be seen as better, as it can literally mean more processing power. But not always, as we'll explore in a moment. Threads, then, are virtual CPU cores, basically. This only applies to x86 processors, by the way, the ones you'd find in desktops and laptops. Mobile and other processors don't use hyperthreading. The term thread refers to the concept of this hyperthreading I mentioned, wherein an x86 processor can split up the physical cores of that CPU into 2 or more virtual cores that can run instructions independently on the same core. Due to the efficiency of modern CPU cores, you can get more performance, literally do more work, by having one core work on 2 sets of instructions at a time instead of just one. If we just stopped here, it would make sense why, at least in a traditional desktop environment, users would chase more cores and more threads for their CPUs, assuming they had workloads that took advantage of multi-threading or splitting the workload amongst many threads at a time in the first place. There are still other factors to consider. Next is what I alluded to at the intro, frequency or clock speed. This is the rate at which the processor can complete an instruction or calculation, measured in hertz or cycles per second. Modern CPUs are measured in gigahertz, where 1 gigahertz equals 1 billion cycles per second. Your processor uses a clock signal to synchronize all of its operations, wherein each cycle allows the CPU to perform a set of actions. This could be fetching an instruction, decoding that instruction, executing that instruction, making a calculation, and so on. All things being equal, the same processor running at 3 GHz will run faster or perform tasks 3 times faster than a processor running at 1 GHz. Things are rarely equal, however. Another physical element in consideration here is the cache, the amount of memory stored on the processor itself to allow for the lowest latency access to process information. The less memory available in cache on a CPU, the more time the CPU has to spend waiting for that information to be accessed from system memory or storage, and thus slower performance as a result. So again, higher frequency, more cache equals better, right? The downside here is that the higher frequency or clock speed that the CPU runs at, the more energy it uses to operate and the more heat it generates that has to be cooled off. This is why many desktop processors can boost upwards of 5 GHz for extreme moments of processing, but they don't operate there constantly. Frequencies tend to fluctuate these days for the sake of energy efficiency and cooling. Then we must also consider node size. The node size for a processor is often referred to in nanometers. You may have heard that this CPU is on a 14 nanometer process, whereas this graphics card has been moved to a 7 nanometer process, and so on. The smaller the node, the more transistors can be packed in any given space, allowing for the processor to be physically smaller and or to have more cores packed in, giving it more performance. Smaller nodes are also closer to one another, reducing latency of communicating amongst each other. Smaller transistors require lower voltages to switch on and off, making them more energy efficient and generating less heat as well. All of this gives you a good idea of what factors determine a processor's speed, and why comparing any of these individual numbers on their own won't give you a true apples-to-apples comparison between processors. There is one final metric that I want to introduce to you that represents your processor speed in a completely different way and can make most of these metrics irrelevant for determining the actual performance differences between chips. IPC stands for instructions per cycle. IPC is a measurement of how many instructions a CPU can execute on average during each of those clock cycles we talked about before. Where clock speed or frequency only tells you how many of those cycles happen per second, IPC tells you the efficiency of those cycles to actually do the work. One could argue that your processor's actual performance is measured by multiplying the clock speed by instructions per clock, and then again by core count, where relevant. Thing is, IPC numbers can vary a lot depending on what the processor is actually doing. We often discuss processors in a broad multi-purpose context, maybe with some notes that video editing benefits from a lot of CPU cores, gaming benefits from some, but not quite as many, and a task like word processing doesn't benefit from very many at all. The microarchitecture of a given processor can actually have accelerations or optimizations for specific workflows, giving those tasks an even higher IPC performance than generalized tasks compared to a CPU without those optimizations. CPUs can also leverage out-of-order execution, where they safely reorder instructions to minimize wait time and increase performance even more, and bigger cache sizes available to the cores can help improve IPC too. A processor with higher clock speeds but lower IPC will perform slower than a processor with slower clock speeds and higher IPC. Ultimately, that's why clock speed isn't super relevant to a CPU's overall performance. The highest speed your CPU can reach is very rarely even used anyway. Under intense workflows, your CPU will spend most of its time running at a more efficient mid-range frequency instead. Let's switch from thinking about traditional desktop processors to your phone that you have in your pocket. Who am I kidding? You're either watching this video on your phone right now or scrolling some other feed on your phone while you watch this video on something else. Or both. As much as a big honkin' 12-core 5 GHz boosting CPU might sound like something that could help your Genshin Impact or Zoombini's frame rate stay high, size-wise it wouldn't fit. It would draw too much power to have any battery life on your phone, even for regular passive use, and it would put out enough heat to melt in your hands. Instead, smaller, more efficient processors have to be used. ARM makes the best CPUs for this purpose. The ARM v9 CPUs used in mobile phones have many accelerations to speed up certain workflows, especially with the SVE2 or Scalable Vector Extension 2 architecture feature. This incorporates new specialized instructions to accelerate key workloads that smartphone users typically experience. For example, SVE2 accelerates HDR video decoding around 10%, allowing users to stream HDR video with longer battery life than ever before. SVE2 can also accelerate multiple common image manipulation libraries, allowing it to give users a smoother experience during video calls and even improve visual quality of those. SVE2 is also vector length agnostic, meaning code development can work on larger vector lengths and enhance additional workloads, such as gaming and AI features. The ARM Cortex X925, which is at the core of the MediaTek Dimensity 9400 for smartphones like the Vivo X200 series, increases the private L2 cache from 2 MB to 3 MB, providing more memory for the processor to access immediately, as we discussed before, bringing up overall CPU performance and power efficiency. These kinds of upgrades allowed the ARM compute platform to deliver double-digit IPC performance improvements in 2024 without cranking up clock speeds or core counts or draining more battery power. This is clustered with the Cortex A725 CPU, which acts as the workhorse, and it has accelerations for AI and gaming use cases where you need more sustained performance over time. This delivered a 35% performance and 25% power efficiency improvement over the prior Cortex A720 CPU. These are substantial gains that come from architecture innovations and IPC improvements, rather than continuing to chase higher clock speeds and higher core counts. Specialized optimization and acceleration like this is what the ARM compute platform delivers in spades, and is required as we continue to make our devices faster while also being smaller, quieter, and more energy efficient. Hopefully this helped you understand how processors work, how their speed is measured, and why just debating clock speeds and core counts is no longer enough, and why performance metrics will be changing rapidly over the next few years in terms of marketing and reviews. To read more about how ARM is powering the future, click the links in the video description. Click this video to see how ARM powers the tech services you use every day to work invisibly for you. And remember to be kind, rewind.